Okay. A pharma team we worked with spent 8 months on an extractable study. Then they submitted to FDA and got a deficiency letter back within 6 weeks, not because their chemistry was wrong, but because the study was scoped from the wrong starting point. They had tested the vial barrel and forgotten the stopper, the plunger, and the needle seal. 8 months of work, a 6-figure budget, and 6 months submission delay from a scoping decision made in 1 week. Hello, I'm Raghuveer Singh Parmar, Director Scientific Affairs at Resolve Mass Laboratories, and we work with pharma and biotech teams to design extractable studies that hold up to regulatory scrutiny. Today, we are walking through 7 of the most costly study mistakes we see and exactly how to avoid each one. The regulatory landscape for extractables has changed substantially. ICH-Q3E, the first global harmonized ENL guideline, reached draft form in 2023. Before that, the teams navigated overlapping frameworks, USP Chapter 661 and 1661 for container performance, ISO 1099317 for medical device pathways, BPOG protocols for biologics, and PQRI thresholds for inhalation products. Multiple frameworks, different scope definitions, different safety thresholds. Most teams don't fail because they ignored the guidelines. They fail because they applied the wrong one or missed where 2 frameworks intersect for their specific product type. Mistake number 1, testing only the primary container. Teams focus on the vial barrel or syringe body and overlook the stoppers, the plungers, needle seals, and gaskets frequently contribute more acceptables than the vessel itself. Regulators review the full contact system, not just the component the drug sits in. Mistake number 2, extraction conditions that don't match the product. Your solvent system, pH, temperature, and contact duration need to reflect what the actual formulation does to the polymer at real stability conditions, not just a generic surrogate. Mistake number 3 is no AET calculated before method selection. Set your detection thresholds first. If you choose instructions before knowing your analytical evaluation threshold, you risk running at sensitivities too low to detect what the toxicologist needs to evaluate. Mistake number 4, a single method analytical battery. GCMS alone misses non-volatile organics, LCMS alone misses volatile, ICP-MS is required for elemental impurities. Each extractables class needs its own tool, and a partial profile in a submission is a gap that the reviewer will ask you to fill after the fact. Mistake number 5 is unqualified methods. Running extraction and analysis without demonstrating recovery efficiency, detection limits in your specific formulation metrics, and method linearity produces results that look complete but won't survive scrutiny. Method qualification data must accompany the extractable results, not appear in a deficiency response 3 months later. Mistake number 6, an extractables report that ends at a compound list. Identifying what you found is only half the study. Each compound says evaluation against TTC, SCT, or compound-specific safety limits. Without that risk assessment, there is no safety conclusion, and without that, the data can't support a submission. Mistake number 7 catches teams off guard. Treating extractable testing as one-time event, material, sterilization, and supplier changes can all alter your extractables profile. Without change control triggers in your quality system, you will miss the bridging study that a changed stopper or syringe component requires, often discovered only at the next regulatory inspection. 3 root causes. These 7 mistakes cluster around 3 root causes. First, design decisions made after the container closure system is already locked, leaving no room to address fundamental scoping or conditions gaps before testing begins. Second, analytical strategy built around instruments already in the lab rather than detection thresholds the applicable guideline actually sets. Third, no extractable subject matter expertise applied at the protocol review stage, no one asking whether the scope is complete, conditions are product representative, and methods cover the AET before a single extraction tube is prepped. Those 3 gaps explain the majority of ENL deficiency later we see. Now, when this mistake reach the regulator, the regulatory consequences are real. FDA 483 observations and complete response letters citing insufficient acceptables data appear across drug products, combination products, and biologics. A biologic sponsor receiving a CRL because extraction conditions didn't reflect the product's pH, a protocol decision made before any testing began. A pre-filled syringe team with a 483 because the plunger and needle shield were never scoped. An inhalation product deferred because no toxicological risk assessment accompanied the compound list. At Resolve Mass, we have supported sponsors through deficiencies that started with a single scoping or methods decision and ended in refiled submissions and bridging studies added 12 months into a program. Now, a framework for a defensible extractable study. Here is the sequence we use for every extractable study we design. Step number 1, scope every contact components across the full container closure system, primary and secondary. Step number 2, define extraction conditions based on formulation pH, temperature, and contact time. Step number 3, build an orthogonal analytical battery calibrated to your AET. Step number 4, evaluate each identified extractable against established safety thresholds. Step 5, embed extractables impact assessment triggers in your quality system before the initial study is closed. Each of these 5 steps closes one of the mistake categories we have covered, and skipping any one is how a defensible study becomes an indefensible one. What should you walk away with today's video discussion? Scope the full container closure system, not just the primary vessel. Calculate the AET before selecting analytical methods. Use an orthogonal battery covering volatile, non-volatile, and elemental extractables. Pair every compound identification with a toxicological risk assessment and build change control triggers so extractable testing stays active across the product life cycle, not just at initial study closeout. Now, in the coming videos, we'll go deeper on toxicological risk assessment and how to apply TTC and safety control threshold. If you're designing an extractable study for an IND, an ANDA or biologics program and need a CDMO or CRO partner in Canada who treats this work as a really scientific exercise, Resolve Mass Laboratories supports small and mid-sized pharma teams from study design all the way through submission. Before I let you go, I want you to subscribe and like this video and subscribe this channel. This would really help us to understand more about your feedback and create more helpful videos for you. Thank you so much for watching this video until the end. See you in the next one. Until then, goodbye for now.